Hello and welcome back. So, we're looking at investigating the sine curve. So, a curve is going to be anything that can be drawn on a Cartesian plane. Remember what we talked about, the Cartesian plane, that being the x-axis, this being the y-axis. Its official name is Cartesian plane, and it's named after René Descartes. So anything that can be graphed on here, and you've been doing that for a while. If you remember your charts that you've been setting up with x and y charts, so if we were to graph a line, you remember, like, if I was going to do y equals 3x plus 1, then I'd put in values here of x. And so negative 2 would go in here, so it would be negative 6 plus 1 is negative 5. Negative 1 goes in for x, so it's going to be negative 2, 1, 4, 7, and then you would graph it over here. 0, 1 is the easiest one for me to graph first, so I picked that one off. 1 and 4, 2 and 7, la 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 la, and we would get a curve. We happen to call that curve a line. Now, you'll also remember that we've done some work with this, so maybe my curve was y equals x squared, so then your table of values would look like x and y equals x squared. We would pick some values for x, and we would then put these values in, and we would sketch them on a Cartesian plane. 0, 0 is the easiest one for me to get, so I do that one first. Negative 1, 1, 1, 1, over 2, up 4, over 2, up 4, and this is the curve that we get. Well, that was called a parabola. So this is a line, this is a parabola, the equation's called a quadratic. So what we're going to talk about today is graphing the curve of y equals sine theta. Now don't get confused, it could also be y equals sine x. It doesn't matter which variable we use here. In either case, you're going to set up a table of values, and we're going to put in values for theta. Now, I'm not going to use negative 2, negative 1, 0, 1, and 2, because when I'm dealing with theta, I usually don't talk about negative 2 degrees or negative 1 degrees. My degrees are usually much larger than this. So we're probably going to be talking things like 30 degrees, and 60 degrees, and 90 degrees, and 135 degrees, or maybe in between I could do 45 degrees. And over here, these would be the answers that I get when I do sine of 30 degrees. Sine of 45 degrees. So I take this value and I plug it in, and I calculate this decimal that comes out. So this one will be sine of 135. So we're going to need to use our calculators. We're going to need to make sure that we're in degrees, and we're going to go through and we're going to calculate. Now, right off the bat, we're going to see here that I have a chart, my degrees along the top, and my ratio is down below. So this is the exact same idea as if I was to go like this. And if I'm going to be graphing y equals sine theta, these would be my degrees or my x-axis. This is going to be my y-axis. I would have my going this way, 30, sine 30, 60, sine 60. But in this chart, we're going this way. So this chart gets turned on its ear a little bit, and it's going to look more like this. We're going to have the theta along the top, and we're going to have the sine theta underneath it. So then it'll be 30 and sine 30, 60 and sine 60. And we're going to go that way instead of this way. So let's take a look at this. If I was to have any sort of curve, like we were talking about before, if I was to take this point here, this would be x comma y. And if I know what the equation is, 3x plus 1, then this would be x comma 3x plus 1. That'd be one way to talk about it. Here, this point here. This point we know exactly is negative 2 comma 4. But if I want to talk about it in general, it's x comma y, very generally. And in this case, y is x squared, so it's x comma x squared. All of that would stand for each of these points. So if I'm going to talk about this, we're going to talk about my point being x comma y. It's going to be the same as theta comma sine theta. Or, as we've said, we're not going to get too upset with that. It could be x sine x. It doesn't make a big deal. So, let's see what we got here. A sine curve can be generated from a circle by plotting the rotational angle. We talked about that in the last video. A rotational angle and the value of sine theta as we rotate. In this lesson, you will graph the standard sine curve by calculating the sine ratio for various angle measurements in degree. Complete the following chart using your calculator and round to 2 decimals. So, we're going to have a chart created. It's going to look similar to this. We're looking at y equals sine theta. So we want to plot all the points, theta comma sine theta. And instead of going this way with theta, y equals sine theta, we're going to go this way. Theta comma sine theta. And we're going to come out this way. And then we're going to take each of those points and we're going to plot them on a Cartesian plane. All right. So here we go. Y equals sine theta. That's our curve. So let's do, these are the degrees we're going to put in. Now I gave them to you. You could have chosen any values at all. I chose these ones. 0, 30, 60, 90, 120. And the ratio that we're going to be coming up with is simply the sine theta, which is the opposite over hypotenuse if we were in a triangle. So let's take a look. 0 sine. 0 sine equals 0. 30 sine, 0.5. 60 sine, 0.866. Now make sure that you're in degrees. If you're not in degrees, then these answers are going to be different, and it's going to be wrong. 90 sine, 1. 120 sine, 0.866. 150 sine, 0.5. 180 sine, 0. Now we come around because I didn't have enough room to keep going. 210 sine, negative 0.5. 240 sine, negative 0.866. 270 sine, negative 1. 300 sine, negative 0.866. Negative 0.5. 0. Notice I finished off the last few without looking at the calculator, because there's a pattern here. There's definitely a pattern. I start at 0 with 0 degrees, and I start going up, positive, 0.5, 0.866, all the way up to 1. Then at 1, I start coming down at the same rate. So so for another 30 degrees after 90, I come down to 0.866. At the same rate, another 30 degrees, I come down to 0.5, back down to 0. So I slowly went up to 1, and at the same rate, I came down to 0. Then from 0, I go down to negative 1, and at the same rate, I come up to 0. So let's sketch that and see what that looks like. So sketch the curve of sine theta in increments of 30 degrees on the axis below. So I see this seems to be bolded, so I'm going to make use of that. This will be my theta axis, also known as an x-axis, but in this one I'm going up by thetas because I've said that my variable here is theta. So we're going to be graphing theta comma sine theta. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300. So that seems to make sense. So we'll go up by 30 degrees, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. And those are in degrees. looking along here, my range, I seem to have a lowest value of -1 and a highest value of 1. So I think I'll make this 0.5, 1, and I think I'll make this 0.5 and 1. This is negative, of course. This is positive. On this side would be negative degrees. Let's start graphing what we have. So this is the point 0 degrees 0. So this will be 0, 0. That's right here. This one will be 30 degrees 0.5. So that'll be here. This one will be 60 degrees 0.8. Well, let's see. That would be 0.75, so 0.86 might be somewhere in here. 90 will take me to 1. I come back down to the same level, so I need to keep those equal. Come down to the same level, come down to 0. So I have this nice curve that's created here. Now I'm not going to connect it with straight lines. I don't believe that's the way it's going to go together if I was to put in a curve of best fit. The curve of best fit looks like this. And it's curved so that it opens down, and then it's curved so it still opens down. That's called concave down. Okay, so it's opening down in a way. Now what happens over here? I go down to -0.5, negative 0.866, -1, same level here, 0 here. Now this curve, we got to be careful. It seems to be curving, so the curve part is facing up. We call that concave up. And we come up to there. And that, ladies and gentlemen, is one complete cycle of the sine curve. Now, if I was to keep going, an interesting thing would happen. You would notice that another 30 degrees, so let's put it in, 390 sine gives me 0.5. So I'm going to go to here. And 410, that'd be the next 30 degrees over. 410 degrees would give me, oh, it can't be 410, I must have done something wrong. So 360 plus 30 more is going to be 390, I was right. 390 plus 30 more is going to be 420. I can't add. So 420 sine is going to be 0.866. So it's going to go back to here, approximately. And then this part right here, if this is 390, this is 420, right there would be 450. 450 is going to give me, what do you think? I have an idea. Did you get one? And it's going to look like that. And what do you think is going to happen? It's going to start to come down. What do you think would happen over here? So if this is 0, and if that's positive 30 degrees, that would be negative 30 degrees. So 30 negative sine gives me negative 0.5. So I'm here. And negative 60 will give me negative 8.66. And you're going to get this. So this wave is a periodic function. This is one complete wavelength. If I was to take this wavelength and pick it up and move it over and put it down here, I'd get the whole pattern going over and over and over. So this wavelength, one period of this wavelength is going to go from here to here, which is going to be 360 degrees. That is going to be your period. Your amplitude is going to be between the max and the minimum. The max that a sine curve can be is going to be 1. The minimum a sine curve can be is -1. So your amplitude will be max minus min divided by 2. So it's going to be 1 minus 1 over 2 is going to be 2 over 2 is going to be 1 unit, which means that it goes up 1 unit from its horizontal and it goes down 1 unit from its horizontal. That's what amplitude means. We've got some important points here that we can see. I notice that if I want to talk about the sine curve in general and very quickly, I could say that it has, at 90 degrees, it's going to equal a maximum of 1. And at 270 degrees, it's going to equal a negative of -1. And at 0, it's going to equal 0. And at 180, it's going to equal 0. And at 360, it's going to equal 0. So if I keep those 1, 2, 3, 4, 5 points, we're going to call those critical points because they're critical to the shape of the graph, where the graph is. If I keep those in mind, I'm going to be able to graph the sine curve very, very quickly and very easily. In fact, if I needed to, very quickly, if I'm walking down the street and someone said, "Hey buddy, can you graph the sine curve?" I could stop and I could say, "Well, yes sir, I can." I would know that it goes up to a maximum of 1, down to a minimum of 1, and I know that it's going to start at 0, 0, and I can remember that every 90 degrees, so 90 degrees, 90 degrees, 90 degrees, 90 degrees, I hit one of these critical points. So 90 degrees, 90 degrees from there, 90 degrees from there, 90 degrees from there. I'm going to hit a critical point. And sine curve starts at 0 and goes up to its maximum. Then it comes back down. Then it comes down to -1. Then it comes back up to 0. So in these equal distances, this is what I'm going to call your critical interval. And the critical interval here is every 90 degrees. So every 90 degrees, something interesting is happening. So, and if I remember that the curve is concave down in that part, and if I remember that the curve is concave up in this part, I can sketch the sine curve fairly easily and fairly accurately. That was pretty cool. There you go. I'm going to stop here and we'll flip the page over and see what's there.